Stanislas Dehaene, you are one of Europe's leading neuroscientists. However, I understand you began your career as a cognitive psychologist. So could you explain to us how you went from cognitive psychology to neurosciences?
Actually, I was trained in mathematics to start with, and then I went to cognitive psychology and then to cognitive neuroscience. I think it's very natural because the field of brain study at the moment is, of course, asking questions that are questions of psychology, like how reading works, but the methods now are largely based on looking at the brain function, using functional magnetic resonance imaging or electroencephalography. So we all have to learn these neuroscience methods in order to ask psychology questions, and finally to frame the results in mathematical theories. So the field is coming together as a very interdisciplinary field, and in my lab, for instance, there are many physicists or many mathematicians.
So that's where psychology, who used to be a soft science, becomes kind of a hard science nowadays.
It's becoming a harder and harder science, actually. Yeah. And if you look at some of the theory and mathematical results, I am very interested in the possibility that psychology will really be expressing strong laws that will be true quite universally across different cultures, for instance.
So you study how culture and biology interact in the human brain, and you have conducted experiments involving our reading abilities and bilingualism. So is there a space or an area in the human brain that is specially dedicated to reading, for instance?
Yes, it's one of the interesting findings in the domain of brain imaging of reading. We all have a certain region in the brain, in the left hemisphere, in the visual system, which, when we learn to read, becomes quite dedicated to recognizing visual words. It's not doing the whole of reading. Reading involves a circuit in the brain, but this region specializes in the knowledge of orthography of words.
Mm-hmm. So this field that is dedicated to reading, does it exist as well in illiterate people?
You mean this cortical area?
Cortical area, yeah.
No, it's quite interesting. We've compared literate and illiterate subjects very recently in a nice science paper a few months ago, and the finding has been that we see this major difference in these particular cortical sites. Of course, the cortex exists in this region in illiterate people, but it's dedicated to something else. It's doing face recognition, object recognition, and what happens is we turn it into another function by learning to read. The term that I used is neuronal recycling. We learn to recycle this region in order to do another function.
So neuronal recycling is a key hypothesis in your new book about reading. Could you tell us about it a little bit more?
So in this book, Reading in the Brain, I propose that we can learn to read because we have a region which we inherit from evolution, whose function is sufficiently close to reading and that we can recycle for this new function. The idea is that we are all primates, and we did not evolve for reading. Reading is way too recent. It's only 5,000 years ago that people have invented reading and writing. So we have to reuse older evolutionary functions of our brain in order to acquire this new feat. And in this particular case, what we do is we recycle areas that have to do with shape recognition, object recognition. Because the brain could not have evolved for reading, I am arguing that reading evolved for the brain. So we can see in the systems of writing throughout the world the same constraints that come from the brain and have constrained, for instance, the choice of particular letters and letter shapes.
So what happens in culture where the written language is made of ideograms rather than letters?
It's a wonderful question. Yeah, we've studied actually Chinese readers and Japanese readers, and the surprising finding is everybody is using the same brain region actually to recognize the shapes of words. Naturally, the grain size is changing, so we refer to phonemes in our alphabet. The Japanese kana system refers to syllable, the Chinese system or the Japanese kanji system refers to small words or word roots, but in fact there is much more universality. because we can find that in all languages there are these two routes. One route to the phonology, the sound system of the language, and another route to the lexicon and the meaning of the items. So if you take French, for instance, of course the alphabet refers to sounds, but there are many irregular words with prefixes and suffixes that refer to the meaning. And if you take Chinese, people think that it's a direct reference to the ideas, but it's not true. There is also a reference to the sound pattern with a certain statistical regularity in the way phonological radicals refer to the sound pattern. So every language makes use of these two routes to the sound pattern, to the meaning pattern, and these correspond to literal routes in our brains. We all have these projections to the sound areas and to the meaning areas in the brain from the visual system.
And speaking of foreign languages, how do you explain that they are good language learners and bad language learners?
This is not completely explained at the brain level. Of course, a lot has to do with how early you learn languages, but in the laboratory, some of my colleagues have found actually that there are also anatomical differences. We can tell from the amount of cortical surface in the auditory system whether you're going to be a good learner or a bad learner, especially for the learning of phonemes of the foreign language. There are some phoneme differences that are quite difficult to make. For instance, Japanese learners don't easily hear the difference between R and L that we all hear. Well, how quickly you can learn this sort of thing is partially determined by how much cortical surface you have in the auditory areas.
Oh, that's fascinating. So we're talking about brain plasticity here. Is there the same plasticity between an adult and a child brain, and between a literate and an illiterate brain?
Plasticity changes in the course of life. We have found that even adults can learn to read, for instance, if they have never been to school but they learn to read by going to alphabetization courses. We see the same sort of brain changes occurring in their brain when they are adults. But we believe that the changes are slower, and we see that from brain lesions in particular. If you're an adult and you have a brain lesion in this visual word form system that supports reading, you will lose the ability to read, and it's very difficult to relearn it. Now, if you have exactly the same lesion in a child, the child will learn to read almost normally using the equivalent area of the right hemisphere. So this is evidence that plasticity is much superior in the child than in the adult. But both can learn, of course.
And about literate and illiterate people?
Well, illiterates can become literate in just a matter of few months. It's a matter of good education. And we will see the brain areas change when they learn to read. These sort of experiments have been done in my lab and in other labs. The key question is, how should we teach them? And I'm extremely interested in exploiting the results we have from cognitive science to design better methods for teaching reading.
So you were referring a moment ago to the fact that we are primates, and from what I understand, there have been experiments with chimpanzees and other apes to teach them at least sign language. So how close are they to the human ability of learning a language?
That's a difficult question. We know they can learn to recognize some shapes of words, either by sign language or by simply written shapes. Even Arabic numerals have been taught to monkeys, for instance. It's a very difficult learning for them, much more difficult than it is for our children. And it's never spontaneous. They will not spontaneously learn a language. It's also never syntactic. So the ability to chain words together into a complicated syntax of a sentence seems to be quite unique to the human brain. And we're beginning to do experiments at the brain level now to try to understand the brain architecture that seems to be quite unique to the human brain. We're seeing that the left hemisphere of the brain plays a special role, but we don't currently understand exactly how syntax is being coded at the brain level. It's a great mystery, I think.
So 15 years ago, you wrote The Number Sense, a book that is now translated into English. This is the second edition. What happened in science during those 15 years between the first and the second editions?
A lot of new science is available in the second edition of the Number Sense. In 15 years, people have looked at the comparison between the human brain and the animal brain with respect to number sense. And for instance, one of the wonderful discoveries that I report in the book is that we now understand how single neurons in the brains of animals code for number. People have made this amazing discovery at MIT that there are neurons that code for individual numbers. So you can find a neuron that will fire in the brain of the monkey when the monkey sees 3 objects. And the neuron will cease to fire if there are more objects or if there is less objects. So it has a sort of tuning curve as a function of number. And we seem to have exactly the same neurons in our brain. That allows us to have a sort of neural code for different numbers, 1, 2, 3, 4, all the way to very large numbers. So that's the basic intuition that is given by our brain about approximate number. And in the book I also report experiments that show how this is transformed by education, and especially what happens to children with dyscalculia. These are children who have specific difficulties in learning mathematics, and we begin to understand that they have these difficulties for many of them because they have early disorganization in these brain areas that care about number. And I end with new software and new ideas in education that might allow these children to progress more quickly in mathematics. I think we've made a lot of progress in understanding how education should be changed in order to provide a better system for children who have difficulties in mathematics.
So these difficulties in mathematics, are they of the same nature, meaning anatomical, as children who have difficulties with languages?
Actually, dyslexia and dyscalculia and also specific language impairments, they are all different deficits that may or may not occur together in children. But some children have just pure dyscalculia. They can read, they can speak perfectly normally, but it's only in the domain of number that they have difficulties. So this indicates that the brain is a modular system. There are different brain areas that care about different aspects of our knowledge.
I'd like to talk about the consciousness in the process of learning. Can we actually learn without being conscious of it? And what would be the cognitive functions related to learning and to consciousness?
Well, consciousness is a wonderful enigma for cognitive science. We now realize that a lot of cognitive processing in the brain is done completely non-consciously. And there are marvelous experiments these days, first that allow us to present information non-consciously. We can flash words or digits and you won't even see them and you believe there is no word at all on the screen, but we can present them. And second, we can track the depths of processing of these subliminal words. And we have been able to show that they go very far in the system, not only at the level of orthography, but also at the level of the meaning of the words. And you mentioned learning. Well, there is evidence for some learning without consciousness. Not a lot, but some. So the great question now for this field is, what is consciousness? What is there more when you begin to be able to see the word? We have an answer to that. It's a tentative answer. The answer is that when you become aware, what we call being aware actually of a word is that the information becomes available for flexible uses in the brain. And that requires a special system in the brain that diffuses the information or broadcasts the information. So this has been called the global workspace model of consciousness. The idea is that we call being conscious a state where the information is no longer specialized, encapsulated in specialized circuitry, but it's made globally available to all of our brain systems. So we can speak about it, we can memorize it, we can use it later, so bring it back from memory, we can evaluate it, and so on and so forth. So we can change our intentions, motor intentions, based on conscious information. So consciousness would be this added flexibility in the system.
Therefore, consciousness would not be only for humans.
Presumably, such a system exists actually in other species, maybe in slightly different form. We are certainly the most flexible species, cognitively speaking. But yes, we are trying to find traces of this long-distance connectivity that allows for this conscious broadcasting in other species. And I'm pretty sure that monkeys have it.
And in your studies, do you touch the question of emotions and the brain?
We've not looked a lot at emotions in my lab. We're mostly looking at cognitive processing, but we've looked, for instance, at emotional words. That was one of the studies of subliminal processing that we did. We flashed these words, and some were just neutral, and others were emotional, like rape or shark or something like that. And we could see that the emotional words contacted a brain structure which is called the amygdala, which is specialized for emotional processing. And this was totally non-conscious. The subjects believed there was no word at all. They could not report whether a word had been presented or not. And yet, this brain system coding for the meaning of the word was being activated. So this was one piece of evidence that subliminal words can go quite far in the system.
And so if you were to present a word that would spark an emotional reaction in one individual, like for instance rape, would you be noting some difference from individual to individual in its response to that particular word?
We don't know to what extent there is variability in these subliminal processing abilities. It's difficult to measure these small subliminal effects, so we have to average across people, and we can't really detect them in individual subjects at the moment. It still is quite difficult.
However, a lot of advertising and marketing is based on subliminal
signals. No, that's not true, actually.
Not true?
No, first of all, in France at least, subliminal advertising is forbidden by law. It should not have been forbidden. It's mostly to reassure the consumers because it's not being used. These effects are way too small to be used in advertising. In fact, in the laboratory we can detect them, but they're barely detectable, and they decay extremely fast as a function of time. After 1 second, there is almost no trace of a subliminal word. So advertisers know very well that it's not the best way to do advertising. The best way is to shoot messages very loudly. So you should not worry much about subliminal advertising. But as a laboratory effect, it's a very interesting effect to track what the brain can do without consciousness.
I see. Well, finally, you are in Vancouver for almost a couple of weeks, and could you tell us what is the purpose of your visit to Vancouver and what you're going to do at the Peter Wall Institute?
So I'm visiting the Peter Wall Institute of Advanced Studies as part of an exchange program with my home institution, the Collège de France in Paris. The goal in both cases is to exchange professors and give lectures. So I'll be giving 3 lectures on my work, and I'll be exchanging with local scientists. And I'll be starting a new book, actually, on signatures of consciousness, which will be the tentative title for a book describing how the brain actually represents a conscious representation.
Well, thank you very much, and enjoy your stay.
Thank you very much.